This is VLSI data conversion circuits, lecture 18. In the last class we were looking at the benefits of oversampling as regards quantization noise reduction in the signal band, and we saw that apart from the usual benefit that oversampling gives us in terms of relaxing the specifications of the anti-alias filter, one can also take a look at the oversampled sequence, right. For example, if this was the input sequence and we knew that it is changing very slowly with respect to the sampling rate, which means that between successive samples the signal is not changing very much, right. The moment you quantize it with a very coarse quantizer, the waveform is probably going to get an approximation to the waveform is something like that. And even visually you can see that if you knew that the signal is changing very slowly, then you can create a signal from the quantized samples, right, where the error between the input and the signal that you have generated, which is a smoothened version of the quantized signal, is much smaller than the quantized signal itself. You understand? In other words, you have a signal, let us say it is a sinusoid, let us call that xn of n. There is now a bunch of samples. Assuming xn is oversampled highly, in other words xn is very correlated from sample to sample. If you quantize it and look at the quantized signal x in q, right, intuitively we saw last time that simply smoothing this quantized signal, right, gets rid of, I mean when you smooth something, what do? I mean you get rid of all high frequency components, and that does not affect our desired signal, because we know that the signal is limited to low frequencies only, right. So if you think of the quantizer as being a combination of, I mean as being an additive noise source, then what we are in principle doing is taking this output sequence, which is the input sequence plus some quantization noise, which we assumed to be white and uniformly distributed and all that stuff, right, and the act of smoothing is basically getting rid of the high frequency components of the quantization noise, while it does nothing to the signal, because the signal lies within the passband of the filter, right. In other words, I mean this is a very loose way of saying that if the signal is varying very slowly, it is so smooth that smoothening it will not change it at all, right. Smoothening is only going to get rid of the rough edges, right. If the signal is smooth to begin with, then smoothening it any further will hardly make any difference. So smoothing is nothing but filtering, okay. So all that I am saying is that by taking this quantized sequence and banking on our knowledge that the input is varying very slowly from sample to sample, the simple act of smoothening, which is a very loose term for filtering. And what kind of filtering must we do? I mean of course it is a digital filter, because this output sequence is a digital sequence. Why is it a digital sequence? Because it is of course already sampled in time. Now the number of levels are also discrete, therefore this can be represented by a finite number of bits per sample. So if the output of the filter is basically a smoothened version of the quantized signal, and the last time around we saw, we actually plotted the error between the smoothened or the filtered quantized signal and the true input, okay, and we saw that it is much smaller than the difference between x in. So, let me, if I call this x in q filtered, right, the error or the mean square value of x in q filtered, I mean with what signal must you compare x in q filtered? I mean ideally you can't compare it with x in, because you know x in there is a lot of delay because of the filter. So, in order to plot these error quantities, what you must do is pass x in through the same filter. I mean this is just a mathematical construction to measure the errors, correct. So, if x in is very deep inside the passband of the filter, which is what it means to say the signal is very low frequency, then this will be x in filtered, and the error, the mean square error between x in and x in q must be larger than the mean square error between x in q filtered and x in filtered. Does this make sense? Okay. And the last time around our filter was a brick wall filter with a band edge of pi by 10. So, and the quantization noise was assumed to be uniformly distributed between 0 to pi. So, we can calculate the in band noise, that is after filtering the mean square noise must be, you will only get that component of the noise within the passband of the filter. Assuming the filter is a brick wall type filter, you get only that much. So, the mean square noise must go down by a factor of 10. Right. So, from this what we see is that oversampling and filtering, okay, it is very important not to forget the filter. It does not make any, I mean it will not really help if you oversample and then you look at the unfiltered sequence. If you simply quantize it, the mean square error will still be equal to delta square by 12, where delta is the LSB of the, or the step size of the quantizer, correct. So, oversampling plus smoothing or low pass filtering will result in a smaller mean square noise, okay. And if this filter is a perfect brick wall filter after the quantizer, so the system basically looks like this. You have the quantizer, then you have a low pass filter, okay. Let us say the corner of the low pass filter is pi by m, where m is some large number, okay. It follows that the signal must be, I mean the maximum frequency content of the signal must be less than pi by m, okay. And then the spectrum at this point at the output of the low pass filter will only be restricted to pi by m. So, in principle even if you downsample it by a factor of m, correct, you are not going to lose any information, right, because there is no frequency content given that this is a brick wall filter, okay. All its frequency content lies between 0 and pi by m. So, in principle one can downsample this by a factor of m and you will therefore get samples at a rate. So, this is sampling at a rate fs, okay. So, what is this the rate of samples coming out at the output of the quantizer at 0.1 fs. What about the rate of samples coming out at 0.2? It is fs, okay. And what is the rate of samples coming out at? It is fs by m, all right. And please note that this is a digital filter, all right. So, it is operating on the digital numbers generated by the quantizer and giving out a digital sequence which can be where you can drop samples and eventually take samples out at the rate of fs by m. Does it make sense? Well, I mean, so if the signal is very low in frequency, it means that you do not need to collect all samples, you can actually drop samples so that you still satisfy Nyquist at the end of the whole process, right. I mean, please note that without the low pass filter, if this low pass filter was not there, then you cannot downsample because there is quantization noise going all the way from 0 to pi, and if you downsample, this quantization noise from outside the signal band will all alias back into the signal, correct. Okay. So, effectively this whole system is looking like a quantizer whose mean square noise is delta square by 12 divided by m, okay, where m is some number, all right. Okay. So, if somebody gave this whole system in a box to you and told you, look, this is a quantizer, obviously because the output is digital, input is analog, go and tell me what the resolution is, what will you do? I mean, what one would do would be to put in a sine wave, measure the mean square error, right, equate that to delta square by 12, from that you find delta, which will give you the resolution of the quantizer, given that you know the full scale, correct. If you did that experiment on this box where instead of having a real quantizer you had this arrangement, then you would be fooled into thinking that the resolution you have inside the box is much higher than the actual resolution of this quantizer, this guy here. Is this clear? In other words, this way of signal processing, which is oversampling, quantization, low pass filtering and dropping samples, okay, is a way of making a poor quantizer look better, all right. you understand. So, let me now mention some jargon. So, this digital filter followed by dropping samples is what is called the decimation filter. Decimation is just the act of dropping samples. So, you are also filtering, and not very surprisingly it turns out that instead of filtering at a high digital rate and then dropping samples, correct, does somebody see any problem with this? Do you think this is a smart thing to do from a implementation point of view? You can't reverse the order because, or rather, I mean, I am not asking you for what the smartest way of doing it is, but at least can you comment on if this is a smart thing to do at all? And what kind of digital filters are you familiar with? Say FIR, okay. So, if you want to get a very sharp filter, what do you think, how many, do you think there will be a lot of taps in the FIR, or there will be very few taps? There will be a lot of taps in the FIR because you want a very selective filter, correct. So, if you have a lot of taps, I mean an FIR filter is nothing but tap delay line, right. So, you delay and multiply and add. So, if you have a lot of taps, it means that you have a lot of multipliers, right, and the power consumption of a digital filter is proportional to the number of gates times the rate at which they are operating, correct. So, if you have, and look at what you are doing here, you have a low pass filter where you are doing this FIR filter, it is operating at the digital rate Fs, and then after you do all this computation, you are saying I need only 1 in m samples, right, I do not need the other m minus 1 samples. I mean then the guy who is designing the filter will say, you know, if you needed only 1 out of m samples, I mean you have told me that before, right, you are making me work unnecessarily hard by making me compute all the m samples, right, and then dropping m minus 1 of them. It is like giving you assignment, I mean 100 assignments and then saying I am going to only take 1 in, you know, every 10, right, without actually telling you beforehand. I am sure you will not be very happy with that, right. So, while it is not clear what the smartest way of doing it is, definitely doing this as is not a very power efficient way of doing things. So, it turns out that you you can actually combine this operation of decimation and low pass filtering into one power efficient unit where both of them are accomplished in stages, okay. If we have time we will go into that, but otherwise that is where I will let it stand, and this is called the decimation filter. There are well established techniques for doing this, where you do sampling rate conversion as well as low pass filter, okay. So, and also as I said before, the ratio of the signal bandwidth to the sampling rate, in other words, if Fb this is the signal bandwidth, the Nyquist rate is 2 Fb, right, is the Nyquist rate, and the actual sampling rate is Fs. So, Fs by 2 Fb is called the oversampling ratio or the OSR, okay. All right. So, therefore, the digital filter therefore will have ideally a cutoff rate corresponding to, in terms of this new jargon, pi corresponds to Fs by 2, the signal corresponds to FB, correct, which in radians corresponds to Fs by 2 is pi, correct, which means that Fb must correspond to pi by oversampling ratio, OSR. Okay, so this is the decimation filter response. I mean, in principle, of course, yeah, once you actually start designing the digital filter, you know that no brick wall kind of response can be realized. Okay, then you can start worrying about how sharp should I make this, and so on, what order will I need, right, and there, I mean, that's all left to the guy who's the digital guy who's designing the decimation filter. Okay, all right. But as far as we are concerned, we can say, okay, digital filter design is a mature thing, everybody knows what to do. Okay, so all that we are going to do is we assume that there is a brick wall filter which goes from 0 to pi by OSR. Okay, so when we integrate noise, we are only interested in that part of the spectrum which is in the band 0 to pi by OSR, and that is called the in band signal to noise ratio or in band signal to quantization noise ratio. Okay. Now, if I double the oversampling rate, so OSR goes up by a factor of 2, what do you think will happen to my in band quantization noise? So, in other words, I have the same signal bandwidth, I double the oversampling ratio, which means that my sampling rate has doubled, correct. So, the question I have is, what happens to my in band signal to quantization noise ratio? What will happen to the mean square noise after I low pass filter it? Pardon?
It will increase by 3.
Increase or decrease? I mean, if your oversampling ratio has increased, do you expect to do better or worse? We expect to do better. So, the noise must reduce. Okay. By how much do you think it will reduce? I mean, if the OSR goes up by a factor of 2, then what happens, as you can see here, is that if you think about it in terms of radians only all the time, then your low pass filter bandwidth has gone to pi by 2 OSR, right. The quantization noise spectrum is flat from 0 to pi, and what will be the density? If it is flat, what will be the height of the spectrum, noise spectrum, assuming it is white and all this stuff? It will be delta square by 12 pi, that is the spectral density, correct. So, within a bandwidth of pi by 2 OSR, obviously the noise power has now gone down by a factor of 2. So, increasing the OSR by a factor of 2 increases the in band SQNR by how much? So, the SQNR goes up by a factor of 2, which is 3 dB. Signal power remains the same, quantization noise power has gone down by a factor of 2, which means that signal to quantization noise ratio has gone up by a factor of 2, which in dB terms is 3 dB. No, 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 it's one sided. Okay. All right. And I mean, if you want to take two sided, then you have to integrate this. This also the filtered noise also from minus pi by. Okay. All right. So you can take this further and say if I increase the oversampling ratio by 4, the SQNR goes up by by 4, which is 6 dB. So in other words, every doubling of the OSR gives 3 dB, or I mean per bit is how many dB? If you increase the resolution of the quantizer by 1 bit, SQNR goes down by 6 dB. So this is giving you 3 dB. So in other words, doubling the OSR is equivalent to improving the resolution of the quantizer by half a bit, or half a bit. So in other words, if you take a bad quantizer and quantize an oversampled version of the input signal, right, you can make it look like a better quantizer than the bad one you used. Okay. And every doubling of the OSR will make that improvement greater by half a bit. So if you want to make a 6 bit quantizer look like a 10 bit quantizer, right, you should increase the oversampling ratio by a factor of 6 bit to 10 bit. It is not 8, it is you are gaining 4 bits, half a bit for every doubling of the OSR. So which is 2 raised to 8, you understand, okay, which is 256, correct. All right. So in other words, based on our simple model for the quantizer, which is an additive noise model, if we take a signal, quantize it to 6 bits, right, but we oversample with an OSR of 256, and then we put a digital brick wall filter which cuts off everything above pi by OSR, and then we throw away samples, right, we decimate it by 256, then the final sequence that we get, right, in terms of quantization noise will be indistinguishable from a 10 bit quantizer. Does it make sense? Okay. All right. So we can see therefore that oversampling does give benefit and makes the quantization noise look lower, in other words make a poor quantizer look great. But now we get greedy and say we are only getting half a bit for every doubling of the OSR. A natural question is it possible to get much more than this, isn't it? I mean, it is a natural question. You say I am oversampling and doing some digital filtering, I seem to be getting some benefit, right, this is good, but will I be able to do? Can I do better than this, correct? So all right. So let us kind of think a little bit and see what we can do. In other words, we try to pick off of our old experience with analog circuits, right, and one thing I would like to remind you is that we know that if we had an op amp, so this is prior experience from negative feedback, right. If we know we had an op amp and we added some noise here, this is V in and this is V out. Let us say the gain of the op amp is A, which is a large number. Then what is V out? V in times A by 1 plus A plus N by 1 plus A. This is well known stuff, correct. We look at this and say, hey, if I now think of this as the quantizer, because after all we replace the quantizer by, we are interpreting the quantizer as an additive noise source, whether it is justified or not is a completely different matter, right. We are assuming that the quantizer can be replaced by an additive noise source, and we say, hey, from my prior experience I know that if I take an op amp based negative feedback circuit and if I inject noise at the output of the op amp, the noise basically does not come through to the output at all, because negative feedback is doing what it takes to keep the output equal to input, correct. And clearly as A tends to infinity, V out equals V in, and noise is completely gone away, correct, which rings a bell and I say, okay, I know that my quantizer is nothing but an additive noise source, maybe I can do this with a quantizer too. Seems like a fair thing to do, isn't it? In other words, I have a quantizer whose output is related to the input by some additive noise source, okay. And taking a cue from this, I just say, now I am dealing with samples, mind you, I put a big gain here, the output of my gain goes to the quantizer, and since we are dealing with samples, please note that any physical quantizer that we eventually plan to build will have some non-zero delay, correct. In other words, if an input to be quantized was given at an instant or at a clock tick n, please note that we are dealing with samples again. So, the more time as we know it is only in discrete increments. So, at the rising edge of clock n, for example, if you give an input to a quantizer, the output is only going to be produced somewhere between, in physical time, somewhere between the nth clock cycle and the n plus 1th clock cycle, but if I am only processing samples, the next time I can look at it is only at the next rising edge, right. This, you must be familiar with this from digital state machines, correct. So, you have some combinational logic, you have flip flops, right. The flip flops clock at say the rising edge and give you some logic that goes and propagates throughout the combinational logic, and the next time you clock it is when you are able to see the effect of the previous decision going through the combinational logic, correct. In other words, the output of the quantizer is not instantaneous, since we are dealing with with the sample data domain. It means that there is a delay associated with it of 1 clock cycle. We cannot get the quantized output at the same instant, correct. So, this therefore is the quantizer, and based on our old experience we just do this, okay, and we say okay, the quantizer I am going to replace by an additive noise source. Let me call that E of n. This I will call U of n, and this I will call V of n. Does it make sense so far? All right. So, now let us go and calculate V of n in terms of U and E, and since the Z inverse, it makes sense to work with Z transforms. So, what does this mean? U of Z minus Z inverse V of Z multiplied by A plus E of Z equals V of Z, which means V of Z times A Z inverse plus 1 equals A times U of Z plus E of Z, which means the output Z transform is nothing but A by 1 plus A Z inverse times U of Z plus 1 by 1 plus A Z inverse times E of Z. All right. Yeah, this is a just correct. So, this is the actual quantizer, because the quantizer output is available only. So, I mean the output is not available immediately, which means that the rest of the circuitry can only process it in the next cycle. Yeah. So, I mean the V of n, you know, you can not V of n, V of n minus 1 is the output of the yeah. So, yeah, a delay does not make any difference. Correct. Yes. Okay. All right. So, is this clear? And therefore, there is a transfer function from the input signal to the output. There are two inputs, one output, so there must be two transfer functions. This corresponds to the signal that we are interested in, and this is called the signal transfer function. And this corresponds to the transfer function from the quantization noise to the output, and is therefore called the noise transfer function. And clearly, as you can see, as A tends to infinity, it seems like U will tend to I mean 1 over Z inverse, which is Z, right, which means that the output comes before the input, isn't it? Okay, which obviously cannot happen, which means there is something seriously wrong with assuming A tending to infinity. Of course, one thing I would like to bring to attention is that both the transfer functions, the signal transfer function as well as the noise transfer function, have the same denominator. That makes sense, because in a linear system all transfer functions will have the same poles. So, that is no surprise. The numerators are different because the inputs are injected at different points in the system. So, where is the pole located? The location of the pole is obtained by finding the roots of the denominator of the transfer function, and that is this, which means that Z equal to minus A, right. So, if you have a discrete time system and if you want the system to be stable, where would you want the locations of the poles? They must lie within the unit circle, right, and where on earth is this pole? This is the unit circle, right, and where is this pole? If you want this to work as we expect, if you want, in other words, if you want it to reject quantization noise, A must be large, which means that the pole is sitting at minus A, which is way outside the unit circle. And the only way to make it work is to choose A less than 1, and sure enough the system will be stable, but it is not doing what we would like it to do. Is this clear? So, this is a unstable system. In other words, if we just did this, the system is unstable. So, then the question let me redraw this in another way. Basically what I am doing is subtracting the input from the output, or rather the output from the input, and then amplifying it by a factor A and closing the loop, and this does not work. And then you say, hey, wait a minute, I want to make this work, but what is the fact that we have not exploited in this whole approach? What is one factor that we have not exploited at all?
Signal is in the lower frequency band, but we have gain throughout.
Very good. So, one key thing to observe is that if we just choose A to be very large, and by definition is independent of frequency, what is happening is that this is indeed becoming 0, but across all frequencies. Okay. But we haven't exploited the fact that our desired input signal is confined only to low frequencies, and in other words, frequencies close to DC. So, therefore, it is only sufficient to have a large gain at low frequencies, and we do not really care what what this does at high frequency. You understand? Obviously, if you make A very large, that seems like a desirable situation, because then you will be able to eliminate quantization noise across all frequencies, but unfortunately that system is unstable unless you choose a very small A, in which case it does not work at all, right. In other words, it is stable, but you have a system which does not reject quantization noise. So, then you say, hey, my signal is confined only to low frequencies. So, why would I want to worry about if A is falling with frequency? As long as the gain A is high at low frequency, that is all I am worried about. Okay. All right. So, given this intuition, and the reason why this is acceptable is because the input signal itself is at low frequencies. Does it make sense? Okay. So, we know now that this must not be chosen to be a large number at all frequencies, we only need it to be infinite at low frequency, meaning infinite at DC, for example, correct. So, low frequency corresponds to what Z? Z equal to, this is the unit circle, DC corresponds to Z equal to 1. So, in other words, our signal is hovering around Z equal to 1, all right. So, what we need is a box here where the gain is high at Z equal to 1. Ideally, we would like the gain to be infinite at Z equal to 1. Okay. So, can you think of a simple lowest first order transfer function where the gain is infinite at Z equal to 1? So, this must be 1 over 1 minus Z inverse. Why? This has got a pole at Z equal to 1, and if you think of it, the impulse response of this structure, this is an integrator, it has got an impulse response of all ones starting at n equal to 0. Now, let us try and evaluate the signal and noise transfer functions of the modulator with this integrator in place. The signal transfer function of Z or Z inverse is nothing but 1 over 1 minus Z inverse divided by 1 over Z inverse by 1 minus Z inverse, and this is equivalent to 1 divided by 1 minus Z inverse plus Z inverse, which means the signal transfer function is 1. The noise transfer function, on the other hand, is 1 by 1 plus Z inverse by 1 minus Z inverse, and this must be equal to 1 minus Z inverse divided by 1 minus Z inverse plus Z inverse, or in other words, the noise transfer function is 1 minus Z inverse. So, we therefore see that the noise transfer function has a response which goes to 0 when evaluated at z equal to 1. And this makes sense because the gain of the forward amplifier, so to speak, which is now an integrator, is infinite when z equal to 1 or at DC. So, for frequencies around a small range around DC, the magnitude of the noise transfer function is close to 0, and at z equal to plus 1, the magnitude response goes to 2. All right. So, where are the poles located now? Z is equal to 0. So, poles are at z equal to 0. Is this clear? So, does this mean that this is a stable system? I mean, you can't get any any farther from the edge of the unit circle, right. So, this is definitely a stable system. All right. Now, therefore, by exploiting the fact that the signal is confined only to low frequencies, and which in turn means that our forward amplifier, so to speak, need only have high gain at low frequency, and the frequency at the gain at high frequencies is not particularly of concern at this point. Okay. We saw that you can in fact realize a closed loop system which is actually stable, and at DC the signal transfer function will be is 1, and more importantly the noise transfer function is, what is the noise transfer function? The noise transfer function is 1 minus Z inverse, and what is the value of the noise transfer function at DC? You evaluate NTF at z equal to 1, which gives 0. This makes sense because we saw that if A was infinite, the NTF would go to 0, correct. Unfortunately or fortunately here, this is only happening at DC, where the gain is infinite. If we move away from DC, what do you think will happen to the noise transfer function? It increases from DC because the gain is falling off from infinity to something lower than that, okay, and therefore the noise transfer function increases. All right.